Hello, this is the first lecture, or the first recording for the Module 7 lecture. In this Module 7, we're going to talk about sampling distributions and the estimation of the mean and the proportion. The objectives for this module is that you should be able to explain what the sampling error is and its effect on estimation. Also, you should be able to explain what a sampling distribution is, what the characteristics of the sampling distributions are, and that, as I said, distributions because there is one for the mean and there is one for the proportion. Also, you should be able to calculate the point estimates for the mean and the proportion. You should be able to calculate an interval estimate for the mean and the proportion. And very importantly, you should be able to interpret the confidence intervals and point estimates that you calculate. And the last topic that we will address in this module is that of calculating the minimum sample size to estimate the population mean and the proportion for a given level of confidence and margin of error. All right, that's what we will learn in this module. The first topic that I'd like to talk to you is about this of sampling error and non-sampling error. This is in section 7.1 of your textbook. All right, what I'd like to start is with an example to explain those concepts. So in the beginning of chapter 5, we looked at the population probability distribution of a six-sided die. And in that case, you might remember that we wrote a probability distribution table where we have the outcomes of the random variable, which are the integers 1 through 6, and the probability of each of these outcomes is 1/6. Here I'm showing you the graph of the probability distribution where there is only probability at each of the integer values between 1 and 6, and the probability everywhere else is 0. Also, using the formulas that we learned at the beginning of chapter 5, here I have the calculation of the mean, of the population mean, mu, which is 3.5, and then the standard deviation, sigma of the population, which is 1.708. Right, so in here, we know everything about this probability distribution. Now, what I like to do, and typically I do this whenever we have a in-person class, I pass out dice, six-sided dice, and I pair you in groups of 2. And then I ask you that one rolls a die and another one records the outcomes of rolling the die. So the objective of this simulation is to estimate the population mean of this distribution of a six-sided die using a sample mean from rolling the die 5 times. And the procedure is very simple. So you roll the die, letting it tumble many times to ensure that we have a random outcome and the outcomes are independent of each other. So once you roll the die, whatever face of the die is upwards, then you will count the number of dots, and that will be the value of the random variable, and that's what you will record. And then you repeat that 5 times. Once you have the 5 numbers of those 5 rolls, then you calculate the average. And then you will continue to do that until you have a total of 10 averages. So you will roll the die 50 times, and you will have averages for each of set of 5 rolls. And then each of you will have a set of 10 averages. Here in the next slide, I have a one set of 10 averages, and averages from each set of 5 rolls. And one thing that you can see is that each of these averages is estimating the population mean. And you can see that some averages are pretty close to the value of 3.5. We have this 3.4 or these 3.6s, or these 2 with 3.6. Also, we get one that is pretty far, 4.2. So then you see that the sample average varies, but each sample average is trying to estimate the population mean of 3.5. So the question is, well, why do we have this variation? And remember that I'm assuming here that there is no errors in recording the outcomes, and there is no errors in correcting the averages. This data that I'm showing you is simulated with a computer, so I know there are no mistakes in that sense. So what you see is the variation in the mean due to what is called sampling error. So it's due to chance, because every group of 5 roles has different numbers, and they occur completely at random. And so the sampling error is just the difference between the average we obtain with the sample average that we obtain, and the difference of that with the population mean. Here we have the luxury of knowing the population mean. For example, the sampling error of the first average, this 4.2, will be 4.2 minus 3.5, that's 0.7. So the sampling error is just the difference between the average, the observed average from the sample that we obtain, and from the population mean. All right. So now, in terms of that particular result, here I have a table where we see that the samples obtained from the same population produce different statistics because they have different elements in each sample. So the sampling error always varies from sample to sample. And one interesting observation is that the sampling error tends to be smaller on average as the sample size increases. For example, in this table, we have the means from 5 rolls of a 6-sided die, and you see that the sampling error, it goes up to 0.7 or to 1.1, relatively large. Now in the second set, these are averages of rolling the die 20 times. So these are the averages of 20 rolls. And you see the sampling error tends to be somewhat smaller. So the highest value is 0.55, negative 0.55. Now here's the averages from rolling the die 50 times. Each of these averages obtained from rolling the die 50 times. And now if you look at the sampling errors, they tend to be much smaller than what we saw in the previous 2 cases. And that is because the bigger the number of observations, the closer the averages tend to be to the population mean. But remember, the sampling error is due entirely to chance, and that's because whatever elements that made it into the sample in a random fashion. So there is nothing we can do ourselves to prevent that. That's just due to chance. However, there are these non-sampling errors that are due to human mistakes made by the humans, either during the collection of the data or recording the data, or when they tabulate the data, when they put it together. So if those mistakes occur, they're not due to chance, they're due to mistakes made by the person putting this, collecting the data, recording it, and tabulating it or putting it together. And one very important component of the non-sampling error is the measurement error, which occurs during the data collection. And measurement error is something that you can, is not often ignored. I mean, people create very intricate protocols for how to collect the data, how to record it, how to tabulate it. But often they forget to look at the measurement error. And for the measurement error, you need to study how to conduct the measurement, write a protocol for how to conduct the measurement, and ensure that the instrument that is being used is calibrated. You may be using a scale to weight things, or you may be using a very sophisticated chemical analysis to quantify composition, for example. But all of that needs to be documented. And at the end, the non-sampling errors, whichever one it is, they bias our estimation. In other words, it gives us the wrong estimate of the population. So it's very important to prevent non-sampling errors. And sampling error by itself there is nothing we can do about it. That is due to chance, and that's just from the fact that every time we take a sample, we have different elements in the sample, and therefore the average for each sample varies due to chance. All right, in the next section, we'll talk about the sampling distribution of the mean.